Here's a fact that surprises many early career engineers: the majority of the cost of software is not in building it. It's in maintaining it. Fixing bugs. Keeping systems operational. Investigating failures at 2 a.m. Adapting to new platforms. Modifying the system for new use cases. Repaying technical debt. Adding features that weren't in the original design. The initial build is just the beginning. And yet, many engineers actively dislike working on so-called legacy systems. Why? Because legacy systems have a particular kind of misery. They may be working with platforms that are now outdated. They may have been forced to do things they were never designed for. The code is full of workarounds for problems that no longer exist. Every legacy system is unpleasant in its own unique way. The book makes a pointed observation: it's difficult to give general recommendations for dealing with legacy systems. But it is possible, and highly valuable, to design systems today in a way that will hopefully minimize pain for the engineers who maintain them in the future, and thus avoid creating legacy software yourself. To that end, the book introduces 3 design principles: operability, simplicity, evolvability. These are the 3 properties that separate systems that are joyful to maintain from systems that are miserable to maintain. Operability means making it easy for operations teams to keep the system running smoothly. The book quotes a memorable observation: good operations can often work around the limitations of bad or incomplete software, but good software cannot run reliably with bad operations. A skilled operations team can patch over a lot. But no matter how well engineered your software is, if the operations around it are chaotic, the system will be unreliable. While some aspects of operations can and should be automated, it's still ultimately humans who set up that automation and verify it's working. So what does a good operations team actually do? The book gives a comprehensive list. They monitor the health of the system and quickly restore service when it goes into a bad state. They track down the causes of problems: hardware failures, degraded performance, mysterious spikes. They keep software and platforms up to date, including security patches. They keep tabs on how different systems affect each other, so a change in one doesn't silently break another. They anticipate future problems and solve them before they occur: capacity planning. They establish practices and tools for deployment and configuration management. They perform complex maintenance tasks, like migrating an application from one platform to another. They maintain security as configurations change. They preserve the organization's knowledge about how the system works, because people come and go, and institutional knowledge can walk out the door with them. Given all that, what can a data system do to support operability? Good monitoring, visibility into the system's runtime behavior. Support for automation and integration with standard tools. Avoiding dependency on any individual machine, so machines can be taken down for maintenance without disrupting the service. Good documentation that follows an easy-to-understand operational model: if I do X, Y will happen. Good default behavior, with the freedom for administrators to override those defaults when needed. Self-healing where appropriate, but with manual override when the situation demands it. And above all, predictable behavior, minimizing surprises. Boring is good in operations. Surprises are bad. Small software projects can be delightfully simple. A new codebase, clean structure, everything makes sense. But as projects grow, they often become very complex and very difficult to understand. The book names this pattern with a term from software engineering folklore: a big ball of mud. A system that started with a clean design but accumulated so many layers of patches, workarounds, and expedient hacks that the original structure is no longer visible. What are the symptoms of complexity? The book lists them. Explosion of the state space: too many things that can be in too many different states, making it impossible to reason about what can happen. Tight coupling between modules: changing one thing unexpectedly breaks something far away. Tangled dependencies. Inconsistent naming and terminology within the same codebase. Hacks aimed at solving specific performance problems that work against the overall design. Special casing to work around issues elsewhere. Why does complexity matter? When complexity makes a system hard to understand, maintenance gets worse in several ways. Budgets and schedules overrun because tasks take longer than expected. There is a greater risk of introducing bugs when making changes, because the developer doesn't fully understand the hidden assumptions, the unintended interactions, the things that will break in non-obvious ways if a certain invariant is violated. Now, and this is a crucial distinction, making a system simpler does not mean making it do less. Klutman draws on a paper by Mosley and Marks that defines 2 types of complexity. Essential complexity: the inherent difficulty of the problem you're solving. You can't eliminate this, it's in the nature of the task. Accidental complexity:
complexity that arises from the implementation, not from the problem itself. This is the complexity that shouldn't be there. It accumulated because of time pressure, lack of foresight, or poor design decisions. The goal is to eliminate accidental complexity while preserving the essential complexity that reflects the real problem. The best tool for removing accidental complexity is abstraction, hiding implementation detail behind a clean, simple to understand facade. SQL is a brilliant example. SQL hides complex on-disk and in-memory data structures, concurrent access from multiple clients, crash recovery, all of it, behind a simple query language. High-level programming languages are another example. They hide machine code, CPU registers, and system calls behind syntax that humans can reason about. The book is honest, finding good abstractions is very hard. In distributed systems especially, there are many good algorithms, but it's much less clear how to package them into abstractions that keep overall system complexity manageable. That search for good abstractions is a major theme throughout the rest of the book. The final principle is evolvability. And the book starts with a blunt statement: it is extremely unlikely that your system's requirements will remain unchanged forever. In fact, they're almost guaranteed to be in constant flux. New facts about your domain emerge. Unanticipated use cases appear. Users do things with your system that you never expected. Business priorities shift. Users request features that weren't in the original plan. New platforms replace old ones. Legal and regulatory requirements change. Growth forces architectural changes you couldn't have predicted at the start. The software development world has a whole methodology for dealing with change at the code level: agile, test-driven development, refactoring, continuous delivery, sprint cycles. All of these practices are about making small-scale code changes less risky and more reversible. The book has a bigger ambition. It's searching for ways to increase agility at the level of an entire data system. Consider the Twitter example one more time. Twitter started with approach 1: query at read time. They switched to approach 2: fan out at write time. How would you refactor a live production system handling millions of users from one architecture to the other? That's not a two-line code change. That's a fundamental data architecture transformation. Evolvability is the property that makes transformations like that feasible, or at least survivable. And the book is clear that evolvability is closely linked to simplicity. Simple systems are easier to modify. Systems with good abstractions can be changed at one level without rippling through every other level. The term evolvability is what Kleppman uses throughout the book, but it's also known by other names: extensibility, modifiability, or plasticity. Whatever you call it, it's the same idea. How much does your system resist or welcome change?